and welcome to Swecodes. Today, we're diving into Leetcode problem 1290, convert binary number in a linked list to integer. This is a fantastic problem that beautifully combines two fundamental computer science concepts, linked lists and binary number systems. Get ready for an exciting journey where we'll transform your understanding of data structures and number conversions. Let's break down what we're being asked to do. We're given the head of a single linked list, and here's the crucial part: each node in this linked list contains either a 0 or a 1. Think of it as a chain of binary digits. The linked list represents a binary number, and our mission is to convert this binary representation into its decimal equivalent. The most significant bit, that's the leftmost digit in binary, starts at the head of our linked list. This is elegant problem design at its finest. Now, let me show you visually what we're dealing with. Here we have a linked list with three nodes, 1, 0, and 1. Notice how the head node, marked clearly, contains the value 1. As we traverse from left to right, we read the binary number 101. Each node points to the next one, and the last node points to null, signaling the end of our list. This binary number 101 equals 5 in decimal. Can you see how the data structure directly represents our number? This visual representation is key to understanding the problem. Let's work through our first example step by step. We have the binary number 101. Watch carefully as we convert this to decimal. The rightmost one is in position 0, so that's 1 times 2 to the power of 0, which equals 1. The middle 0 is in position 1, so that's 0 times 2 to the power of 1, which equals 0. The leftmost one is in position 2, so that's 1 times 2 to the power of 2, which equals 4. Adding them all up, 4 plus 0 plus 1 equals 5. Always remember to consider the simplest possible inputs when solving problems. Let's crystallize what we're really solving here. We have 3 clear steps. First, we receive a linked list where each node holds a binary digit. Second, we need to traverse this list and read the binary number from left to right. Third, we convert this binary number to its decimal form. This is a classic example of a linked list traversal problem combined with number system conversion. Understanding the problem type helps us choose the right approach. Here are 2 powerful hints to guide your thinking. First, remember that in binary, each position represents a power of 2. When you move from right to left, you're dealing with 2 to the 0, 2 to the 1, 2 to the 2, and so on. This is the foundation of binary numbers. Second, and this is where it gets interesting, you can use bit operations for an elegant solution. The left shift operator multiplies by 2, and the OR operator adds bits. These operations give us O(1) space complexity. That's the mark of an efficient solution. Let's think through this problem systematically. Step 1. We need to traverse the linked list from head to tail. That's our data access pattern. Step 2. At each node, we extract the binary value, either 0 or 1. Step 3. We build our decimal number incrementally as we traverse. Step 4. Here's the key insight: each new bit we encounter effectively shifts all previous bits to the left. This is because reading from left to right means each new digit is less significant than the ones before it. This thought process leads us directly to our solution approaches. Our first approach is the brute force method using string conversion. Here's the algorithm. First, we traverse the entire linked list and build a string containing all the binary digits. Then, we convert this binary string to a decimal number. This approach is intuitive and easy to understand, perfect for interviews when you need a working solution quickly. The time complexity is O(n), where n is the number of nodes, but notice that the space complexity is also O(n), because we're storing all digits in a string. This extra space usage is what will improve in our next approaches. Let's see the code implementation for both Java and Python. In Java, we use a string builder to efficiently build our binary string as we traverse the linked list. Then we manually convert from binary to decimal by processing the string from right to left, using math.pow to calculate powers of 2. In Python, the solution is even more elegant. Python's built-in int function can directly convert a binary string to decimal when we pass 2 as the base. Notice how both implementations follow the same pattern: traverse, build string, convert. The comments in the code guide you through each step. Now, here's where we level up our solution. The key insight is that when reading binary digits from left to right, each new digit means we multiply our current result by 2. Think about it. If we have 10 in binary and we read another one, we get 101. The original 10, which is 2 in decimal, becomes 100, which is 4 in decimal. That's multiplication by 2. So our formula becomes result equals result times 2 plus the current bit. This approach calculates the decimal value on the fly without storing the entire binary string. Look at how clean this implementation is. In both Java and Python, we simply maintain a decimal variable that starts at 0. For each node we visit, we multiply our current result by 2 and add the node's value. This single line, decimal equals decimal times 2 plus current.val, does all the heavy lifting. The beauty of this approach is that we've achieved O(1) space complexity while maintaining O(n) time complexity. This is a significant improvement over our string approach. Now for the most efficient approach using bit operations. The left shift operator is essentially multiplication by 2 at the bit level. When we shift 5 left by 1 position, we get 10, that's exactly multiplication by 2. The OR operator then adds our current bit. So instead of decimal times 2 plus current bit, we can write decimal left shift 1 or current bit. This is not just elegant, it's also how computers naturally handle binary numbers at the hardware level. Here's our bit operation implementation. Notice how similar it is to approach 2, but we've replaced multiplication with left shift and addition with OR. The expression, decimal 1, current.val is the heart of this solution. While the performance improvement might be marginal in high-level languages, this approach demonstrates deep understanding of computer science fundamentals. In systems programming or embedded systems, such optimizations can make a real difference. Let's compare all three approaches. String conversion, O(n), time and O(n), space, easy to understand but uses extra memory. Direct calculation, O(n), time and O(1), space, the sweet spot of simplicity and efficiency. Bit operations, O(n), time and O(1), space, the most efficient, showing mastery of low-level operations. For interviews, I recommend starting with approach 2 as it balances clarity with optimal complexity. You can then mention approach 3 to demonstrate deeper knowledge. Remember, the key insight was recognizing that reading binary digits left to right means multiplying by 2 at each step. This problem beautifully illustrates how understanding the underlying mathematics leads to elegant solutions. Keep practicing, keep learning, and remember, every complex problem becomes simple when you break it down step by step. Happy coding!